Hello, everyone. Thanks for joining us at SpaceWaves. I'm Mark Zastrow, a senior editor at Astronomy magazine. And next, I'm going to be speaking with two researchers who come from different fields, but they're both doing work on the very hot topic of space sustainability, particularly satellite megaconstellations and some of their unintended consequences. So, one of those consequences is the impact of having all these satellites in the night sky related to light pollution. They can reflect a lot of light visually, and also they leave streaks through the images that are taken by telescopes, which can seriously compromise the effectiveness of astronomical research. Another unintended impact is what happens to all of these satellites when they fall back to Earth and burn up in the atmosphere. And a growing number of researchers are concerned that using the atmosphere as an incinerator to dispose of satellites could have environmental impacts, including on the ozone layer. So joining me now are Meredith Rawls, an astronomer and research scientist at the University of Washington who studies stars and astrophysics, and José Pedro Ferreira, a Fulbright and NASA doctoral fellow in astronautical engineering at the University of Southern California, where he studies the environmental impacts of spacecraft demise in the atmosphere. Turn a phrase that I find incredibly evocative. So thank you both for joining us.
Thank you, Mark.
Thank you.
So Meredith, I'm going to start with you. When did you and the astronomical community first really become aware of the impact of satellite constellations like Starlink? And what was that realization like?
So some astronomers have been paying attention to satellites for quite some time, and they are radio astronomers because not only do satellites reflect light in the optical, but they also emit in the radio. And for quite some time, there's been a lot of coordination required for spectrum sharing and who's allowed to broadcast and transmit where. But only more recently, in about 2019, early 2020, around when the pandemic began, to be honest, did the growing number of low Earth orbit satellites really show up on a lot of optical astronomers' radar, including myself.
And so was there a moment when you saw any images or when maybe you yourself saw anything in the sky and realized that this was kind of going to change the direction of the field?
I did realize this was going to be changing the direction of the field when I saw the image from the dark energy camera and the Blanco 4-meter telescope in Chile. And it's kind of iconic almost. And it shows a bunch of, I think, more than 12 satellites just streaking across it, leaving these bright trails, kind of blocking our ability to do science on all of the stars and other astrophysically interesting things. It was coincidental. No one was trying to observe the satellites. It was part of a larger observing plan for that night. And it is it has become kind of a touchstone for representing the problem in the optical. So much so that when I recently visited Washington, D.C. and went to the National Museum of Natural History, they actually have an exhibit there on light pollution. And there's a small corner in this outstanding exhibit on light pollution that talks about satellite constellations. And they have this image there to kind of illustrate the problem.
Wow. So it really has become a kind of iconic environmental awareness, kind of bringing awareness of a change in our environment, like so many other sort of iconic images in the environmental movement in a way.
Yeah, unfortunately, that's the case. Yes, it's like any kind of defining moment. It is not the only example, but I think that around that time is when many astronomers started to pay attention and say, well, wait, are there any rules on how many satellites companies can launch? Are there any limits on how bright they can be? Like what is realistically going to happen? Is this even a viable business model? Or is it just going to be, a few dozen things and we can all move on with our day? And even though it's been 5 years, there's not a lot of consensus on all of these questions because no one has a crystal ball, right? No one can predict the future. But so far, the future has definitely included line go up when it comes to the number of bright satellites in orbit around the Earth.
Pretty much a hockey stick type diagram. Yeah. So you're involved with the Veris C. Rubin Observatory, project of the National Science Foundation and the Department of Energy. One of the biggest funding priorities in astronomy for these agencies, been in the works for 25 years. Can you talk a little bit about why this telescope is such a big deal and how it's going to be impacted by the issue of satellite streaks?
So Rubin Observatory is amazing. It is this new facility. It's going to come online near the end of this year, and it's going to take a high-resolution movie of the night sky and revolutionize pretty much every area of astrophysics. Things that change in the sky, things that are really faint in the sky, helping us understand cosmology, how our solar system has come together, pretty much all of it. And I am really honored to be part of the team that helps with some of the software development and data pipelines for this observatory. Related to that, we are certainly keeping track of this issue. And to the best we can tell, Rubin is going to be affected by satellite constellations because it is in fact looking at the sky, and satellite constellations are in fact in the sky reflecting light. But it's not catastrophic. We're still going to be able to do amazing science. There's a lot of work happening to make sure that we can mitigate the effects from multiple different angles, and we're still going to be able to do really great science.
It does mean a lot of work, though, I'm sure, for you. I know you're involved in the data pipeline, so producing the software that all of the images are going to be processed with. I mean, how much of your time are you actually spending of your research time studying stars and astrophysics, and how much are you actually working on trying to remove these streaks from the images?
Sure. I think it's fair to say across the board that astronomers are having to spend more time than we would like dealing with the fact that there's this new source of noise and contamination in our data products, right? This is not unique to Rubin necessarily, but it certainly personally for my own career, I do spend a significant fraction of my time on satellite mitigation activities. And that is largely through there is an International Astronomical Union Center that formed a few years ago. It's called the Center for the Protection of the Dark and Quiet Sky from Satellite Constellation Interference. We did not pull a short name out of the hat. But in particular, there's a portion of this center called SatHub that I co-lead. And the mission of SatHub is to basically enable collecting data and better studying the problem of satellite constellations so that all ground-based astronomy, including Rubin, can use the data that we have and the connections that we make with satellite operators and different industry people who are experts in their various areas to quantify the problem, to mitigate the problem, and to just actually talk to one another, because that can sometimes be the most challenging thing when this is such a new problem.
Right. Well, thanks so much for that. José, I want to turn to you now. So we're sort of talking about the hockey stick graph of how many satellites are now orbiting Earth and how that's increasing at an exponential rate. And probably a lot of the people who are watching this may have seen, a train of recently launched Starlink satellites go across the sky personally. But so in addition to these, the visual aspect of this and the optical and the radio, there are all these concerns about what happens when these satellites re-enter the atmosphere. Can you give us a kind of a basic rundown of why there are so many satellites that are beginning to re-enter the atmosphere now?
So this is in some way a race between the lifetime of the spacecraft, the trend for miniaturization of technology, the rapid turnaround between how fast you put new technology up there and how fast it will re-enter, and of course the trend for distributed systems in orbit that will of course reduce the risk, but will also provide coverage worldwide for telecommunications, for example. This is essentially the reason why we now have more objects in orbit, arguably with less mass. So each individual orbit has a lower mass. So that's why the hockey stick in terms of number of objects doesn't really match that well with the actual mass that is launched into orbit. You see that's a noticeable increase, but it's not an exponential one in terms of mass. We can also look at other points of view, for example, as cross-sectional area, and that will also play a role in terms of how it reflects radiation and what's the probability for collision. But to answer your question, why do we predict that we will have so many objects re-entering in the next 10 years, for example, is one, due to the increased number of the launch cadence, the essentially the providing the infrastructure in orbit for these mega constellations, which have a much more reduced lifetime. They will re-enter faster than what usually monolithic satellites will tend to do, and most of all, they also abide by new rules for the orbiting. So there was this international guideline that strongly promoted and encouraged a 25-year deorbit rule, meaning that the satellite would need to decommission from orbit and re-enter in the atmosphere in order to protect the orbital environment, declutter the orbital environment within 25 years. The FCC mandates right now not encourages, mandates a 5-year rule for the orbit, which means that every single entity operating out of the US would need to deorbit their satellite in 5 years. This is in some way another race between decluttering the orbital environment, but then also paying attention to what are the consequences not only on the ground but also in the atmosphere. We may also argue that we actually want most of the mass to demise in the atmosphere, because that means that nothing will get to the ground. And in that way, we are reducing the probability of impacting people and harming people on the ground. And that's totally true. So this is, again, a trade-off between how much gets to the ground, how much stays in the atmosphere, and what is the response of our natural systems, of our ecosystems, to this kind of consequences, because there's definitely not a silver bullet that will miraculously clean the orbital environment. But certainly the focus now is to further understand the consequences, the impacts in our ecosystems.
And so just to put some numbers on that, for instance, Starlink, I believe SpaceX has applied for 42,000 satellites in that constellation. And so that 5-year rule means that 42,000 satellites must deorbit every 5 years. Is that correct?
It depends on the constellation per se. It depends also on the operator and on the country that the company is operating for. And bear in mind that different countries have different national laws that the company would need to abide by. But the rule of thumb is that with the miniaturization, with the reducing the lifetime of the spacecraft, we are expecting to see an increase of re-entry rates due to the increase of the launch rates to orbit. And logically, we would also expect to see other countries to adopt these diminished life or this diminished timeline for re-entries upon mission termination. I think that would be expectable to see in the forthcoming future, and that of course will contribute to these impacts that we need to further understand.
Right. Of course, it's not just SpaceX and Starlink. China has multiple mega constellations that they're launching right now as well. So yeah, it's a global issue, or going to be. So can you give us kind of just a basic rundown then of what kind of numbers we're talking about? How much of these metals are being vaporized? What is the basic issue here in terms of what we're injecting into the atmosphere by incinerating all of these satellites?
So I usually like to start this sort of reasoning by baselining what is already there. So our atmosphere is formed by the contribution of different factors. From when the Earth was a protoplanet, that the gases started to accumulate due to gravity, and then also the bombardment of micrometeoroids that changed across time the composition of our atmosphere, among other factors. So the baseline is that we currently have a flux of micrometeoroids into interstellar dust that re-enters the atmosphere, and that contributes to the natural balance of the atmosphere with a given chemical composition. And this is essentially our baseline. This is what I call the natural contributions. And essentially, we are concerned if there is any change to the status quo, then there is an impact. We don't know if there is a positive or a negative impact, but there is for sure an impact. The way I define an impact is a change in the status quo. So it turns out that that essentially anthropogenic sources of metals, such as satellites, such as upper stages of launch vehicles, and so forth, bring into the atmosphere metals that are not naturally occurring, point one, and point two brings higher concentrations of metals that are already occurring. And this is the point at which then we start, ringing the alarm bells and say, hey, we need to really look into this, because we don't know what's the long-term impact of increasing these values above natural levels. In this realm, and then I'm sure you'll be able to find different researchers pointing to different estimates. It depends on the orbital debris model, evolutionary model that they would use to estimate re-entry rates and so forth. But as of now, in my research, the point that I'm mostly concerned about is with regards to aluminum, mostly because it's the dominant species in aerospace structures. So spacecraft structures and launch vehicles, they are mostly made out of aluminum alloys, and it has been suggested that it can have a plethora of different impacts, from impacts in radiative forcing, which means whether or not these particles will reflect radiation that comes from the sun or trap radiation within the Earth.
So that's impacts on climate, potentially.
Correct, yes. Another face of this coin would also be the potential impacts in the stratospheric ozone that was also actually studied in the late 90s with a direct injection by rocket launches in the stratosphere, and this being a different source, given that it comes from above, from the mesosphere. And another point that also concerns a lot atmospheric scientists is the impact of these microparticles in the formation of high altitude clouds, which are once again not very well understood because of essentially the sheer magnitude of the altitude at which these phenomena take place. These altitudes of 50 to 80, 90 kilometers are very difficult to gather data from in situ. And that's basically where all the question marks came from or come from, are the uncertainties about what do we know about the microphysics and chemistry at these altitudes that lead us to ask the question, what are the long-term impacts in climate, in the atmosphere from these re-entry events? But the fluxes that come from orbit, that we can estimate with some degree of certainty, and that's what points us the way to ask these questions.
The questions of what could actually the impacts be? Could they be bad? Could they be not bad?
Exactly.
And so right now the jury is still out, and this is something that right now researchers are focusing in on.
I would say that's the starting point. The initial conditions are that are concerning in terms of what re-enters, the fluxes that re-enter in the atmosphere.
Because they're so much higher than the natural levels.
Exactly. To answer your question and focusing on the numbers I've crunched with regards to aluminum, I'm very comfortable to say that the amount, and this is a very conservative estimate, but by the way, that the amount of aluminum that re-enters from a low Earth orbit as of last year matches the one that re-enters from micrometeoroids, and this is not even considering phenomenon like differential ablation and other sorts of more intricate phenomena that we could and should pay attention to. So very conservative, and basically, if we see that the fluxes double, if the anthropogenic contribution doubles the one of natural sources, this points us to ask the question whether the atmosphere is able to take it or not in the long term.
And what would the potential consequences be? For aluminum, I take it ozone is one of the concerns. How the loss of ozone, how would you compare that to kind of, the issues that we had in decades past, when we had an ozone hole that is still recovering? Can you make a comparison at this point?
It's very hard to make a comparison because first and foremost, there are several impacts that we can list down, as I mentioned earlier. Impact in radiative forcing or global warming, if you want to use a broader term. Impact in high altitude cloud formation, and the one you were mentioning about stratospheric ozone depletion. When we talk about stratospheric ozone depletion specifically, the mechanism, although it's not the same, it's analogous to what happened in the past. Which, I mean, in the past we had a flux of chemicals that were ozone depleting, in the sense that they came from below the stratosphere, and they ascended, and then they had some sort of impact in the ozone depletion cycle, and this one essentially comes from above. So, but in terms of broad terms, this would be the mechanism that we would need to further understand, because again, the dynamics of how it settles down in the atmosphere, how it interacts with the gases around it, how the aerosol is formed, are still very, very poorly understood. In comparison with what happened in the 80s, I mean, the process was exactly the same. We needed to further understand what was happening in order to get to a broader agreement with the Montreal Protocol to banish those chemicals. I would say that first and foremost, we need to further understand whether there is indeed a negative impact before we regulate in that terms. But in case we do find, of course, action is needed. But my point here is to pass the message that there are a lot of unknowns that we should focus on in measuring in these high altitudes. But bearing in mind that the pieces of evidence are at least concerning.
Got it. Well, let me ask to both of you then. Outside of looking to the communities outside of your own research communities, how are you working with industry, working with regulatory groups to try to work these problems and better understand them, or in some cases create solutions for them? So Meredith, what is the working relationship like between astronomers and satellite operators?
So we actually have some pretty good precedents of astronomers working with some satellite operators. But as you pointed out, there's just so many people entering the scene. And we don't really have the person power to scale up like one-on-one conversations with every single new player who starts deciding to launch their own constellation of satellites. So it felt early on, it felt like with SpaceX being the one that was the kind of leading this wave of constellations, they actually have been very responsive to astronomers and have done some darkening mitigations that have really been helpful, and in some cases actually makes it a little harder for them to get like maximal solar power. They're willingly pointing their spacecraft in a slightly different orientation to minimize some glints down to Earth, and not like maximize their power. So we're very appreciative of that. They are not required to do that. And they've put time and energy into developing a specular reflective coating that can reflect sunlight. Specular just means like a mirror. And so when I first heard that they were making them shiny, I was like, how is this mitigation? But it actually sends the sunlight away from the Earth direction. And so I guess if you were, out further in higher Earth orbit looking, you might see lots of glints from these satellites. But at the moment, that's not a concern. So the amount of flux that comes down to ground-based observers is less most of the time. If they have to do a weird roll or orientation, you get like flares and glints, which is potentially also an issue. But so this dialogue has been going for several years and has generally been very remarkably positive. And then we have relationships established with several other satellite companies as well. But it's just a lot of this is volunteer-based work on both sides, and there's really not a good framework right now for trying to grow that, especially when you start having a lot of different international things to consider, and you don't always have the ability to call up your buddy who happens to work at SpaceX, because enough astronomers know enough people, right? And it's not quite so straightforward, so it's definitely a challenge.
So what does a regulatory framework look like to tackle this broadly, so it's not just ad hoc relationships?
I wish I had a magical answer for an international regulatory framework for low Earth orbit, Mark. That would be great. If you find one, you let me know. I mean, so the UN is like one avenue, right? But they move extremely slowly. Like you have these different timescales, right? You have these satellite operators that are just move fast and break things. You have academia who is like slow in comparison, right? Oh, let's like wait and see. Let's do the study. Let's assess this change in status quo. Let's, notice that there has been a change. Let us, now take more data to derive a conclusion, right? And which is wonderful. I love science, but it's not as fast as the tech innovation side. And then over on another planet, you have regulatory agencies, which are often, bound by national country-based jurisdictions, yet satellites orbit the whole globe. So it's not, and a lot of this is set maybe from the country that is launching the satellite or the country that is formally operating the satellite, but realistically, they go over the whole Earth every 90 minutes. So to get anything that is like meaningful, it needs to be some kind of international basis. And so to this end, the UN has a committee for the peaceful uses of outer space, and they have for the first time, I believe last year, possibly 2 years ago, agreed to hear an agenda item about preserving our dark and quiet skies, which is wonderful, but is also not a regulation. It is acknowledging that there is an issue that is worth learning more about, which, good step, important step, slow step.
First steps. Jose, what is it like on your side? Are these kind of conversations happening between yourself and researchers doing the work that you're doing, and industry and regulatory bodies?
Well, I would firstly say that I totally second Meredith's point of view in the sense that we need to talk to each other. We need communication lines. We need open pipelines to talk about this openly, to increase the rate at which we make progress. I would say that the first point to look at, and this is something that I've seen a huge improvement in the last couple of years, are the open communication lines between different research areas in academia. The problem of reentry and understanding the aerothermodynamics and how the satellites and how these bodies demise upon reentry is highly multidisciplinary. So we are crossing different domains of knowledge, perhaps 70 or 80% of the domains of technical knowledge there is. And usually these areas are very much compartmentalized. So there are the aerospace engineers, the material scientists, the chemists, the atmospheric scientists, the experts in aerothermodynamics. And bringing all these critical mass, these subject matter experts together to discuss this problem is something that I started seeing happening a couple of years ago, and I'm very proud that we are now moving in the right direction. Is this fast enough? Perhaps not, but it's a step in the right direction. So there is now this almost open resonance box where we discuss ideas, and we think that we're going in the right direction in terms of how to measure the problem, how to postulate the problem, and how to actually get to an answer to how we're going to figure out about the environmental impacts in the end. Now, about the pipeline between academia and operators. This is something that needs to be mediated, and there needs to be a platform for that to happen. I believe in academia and on the research side, we are responsible to provide data and to make it clear and verifiable and trustworthy. This is the mission that I consider academia is responsible for. Then, of course, there is the storytelling part, which I believe we are also responsible for, which is we're not only communicating new conclusions clearly, but we are also making it accessible to the public. And this, of course, will push for policy development, and this will bring a call for action. So this is what I see as mission from on the scientific research side. This is the agenda to put forward. It is something that I also take as a personal mission, if I may say. But in terms of an open communication line between academia and the operators, I don't think that these two bodies would be responsible for any action. There's got to be a middle ground player, which is actually the decision maker. be it a government, be it an intergovernmental body such as the United Nations that would need to make the decisions and make them applicable to in terms of law. That's usually how things work in my perception. We reach the conclusions, we develop policies, and then we implement it so that people abide by them. And this is, I believe, the path that we are going through. And again, in the academia, I believe we are working towards providing the data to push this agenda and to push this vision forward so that policymakers can make their own decisions.
Sure. You mentioned the interdisciplinary nature of this issue. I'm curious. Okay, so now we have an astronomer, we have an astronautical engineer together. Do you have any questions for each other, having listened to each other talk about their perspectives of the problem?
Actually, perhaps the first question that comes to mind, and not that I haven't asked this question to my astronomer friends, but I would like to have to take your point of view. Do you have any sort of model you could use? Do you model the constellations around the globe so that you can predict when they are more reflective and when you can actually make your measurements? Is this something that you plan for, or is it even possible for you to plan for it, provided that the two-line elements like the orbital elements are available for you? So is this something that you can prepare for, or you're just reactive to it? You just see that your data is corrupted and then you just go after and you try to solve the problem afterwards?
That's a great question. It's both. It started off very much as oh my God, there's a thing in my data, and we are slowly pushing towards actually being able to proactively predict some of this stuff. The challenges are you nailed it, right? TLEs, the two-line elements for kind of forecasting satellite positions, are notoriously inaccurate and imprecise, and the ability to actually model like the physical surface of a satellite and how bright it will reflect in some given wavelength of light is quite challenging. You can't really parameterize it down like astronomers like to pretend that everything is a very simple sphere that just radiates evenly in all directions, and that is like super not what happens here. The darn things move. They don't have a star-like response on our detectors. It's very annoying. So it's a combination. And we do have some folks who are working a little bit on improving the brightness modeling, but it's limited to having a basic understanding of the physical satellite itself, which is not always information that companies are willing to disclose, which can be a challenge, as I'm sure you've encountered in your own way, trying to figure out what the heck these things are made of.
Yeah. So they are required they are required to release the TLEs, correct? So that is something that is out there, but you're saying it's much more complicated than just getting the TLEs and being able to predict where exactly they're going to be.
Yeah. Yes. The TLEs, I think that it's required. I'm not actually sure what degree of
Right.
I don't think it is required.
It's kind of
there's
standard
a network
practice
of observers that basically keep track of where things are if they can see them at all. And this is in the US at least, this is now becoming the responsibility of the Department of Commerce's Office of Space Commerce. It was previously part of the Department of Defense, and they kind of got tired of keeping track of all the commercial space trash as a side hobby. But basically, the Department of Space Commerce is now in charge of maintaining a catalog of all of these different things in orbit and serving that to the public. And they're developing some software to do it a little bit better. Kind of independent of that, there's a few different folks who are working on higher precision telemetry or position forecast. And that is largely coordinating with aerospace type companies that have their own set of monitoring telescopes around the globe. So a lot of this information is actually not coming from the operators themselves. Some of it is, but a lot of it is coming from these independent network of small telescopes that are either privately owned or part of the government efforts to keep track of what the heck is up there. And then into many cases, that information is then sold to like make a viable business model for the companies that have these networks, so that the operators themselves can know where their things are and not run into one another. And which is a space debris collisions is a whole other area we haven't even touched. But that really relates to the whole sustainability of how we use space, larger conversation. Yeah, I guess the to come back with a question at you, Jose, I wonder, like, what would you suggest for some kind of sustainable space framework? Because we don't want to, the 5-year rule is tricky, right? Because we don't want to leave stuff up there forever in a higher orbit or send it to a graveyard orbit like we used to and be like, oh, it's now super high altitude and it will never come back to bother us ever again. And it's just like, that's not how taking out the trash works. But the atmosphere is not our garbage disposal either. I mean, aside from the easy answer of don't launch so much stuff, do you have some idea for some kind of middle way?
Mm-hmm. That's a million, or I would say the $1 billion question. But let me first go back to your TLE point with regards to, I mean, even if you know where the object is, knowing the orientation, and as you mentioned, knowing what the object is made of and the reflectivity of the object completely changes your capability to predict or forecast whether your measurement is going to be impacted while doing it from the ground. So that's definitely a very complicated process for prediction. But thanks for sharing, because I was not aware of the full loop. The full feedback loop of what you need to do to predict, and then you need to react because you were actually impacted your measurements and you're probably not expecting it.
Yeah.
That's a very good.
In practice, what we will probably do for some of the largest ground-based facilities that really don't want to observe the brightest things is we will just have a list of like 24, maybe that's optimistic, maybe it's 100, I don't know, of the ones that are just known to be really bright. Right, like there's these new Bluebird satellites that were recently launched that are these like tennis court sized unfolded direct to cell things, and they are just gonna be extremely bright, and we just don't want to point really sensitive ground-based telescopes at them, not because they necessarily would be damaged, but just because it would ruin the majority of the image. So like, let's not. And so I think the like kind of practically implementation wise, we're gonna have this list of known too bright to look at things, and we will do our best to keep tabs on exactly where those are each and every night, and then adjust our observing strategies accordingly. So like if you really wanted to observe this galaxy, but you run this little program to be like, oh, is the bright stuff going to be in the way? Then you just, wait an hour or 20 minutes or whatever you need to be. It's like I like to think of all of the satellites kind of swarming around the Earth as like bugs on the windshield for these large ground-based telescopes, right? And so that if you know that you're not plowing through a storm or a swarm of them, it's workaroundable. You can still see where you're going, but you can also do some thoughtful mitigations to maybe not go through the clumpiest area. Anyway,
makes total sense. Now let me get back to your question, because I don't want to leave you unanswered. Not because, I mean, it's a very tricky question. There is no simple answer to it. But what basically I wanted to share with you is a framework of how to approach it, and let's just assess the different perspectives we can look into the problem, and see how it can go from there. So we can actually start looking at these environmental impacts from the get-go, from the design stage of a spacecraft. We can implement some sort of a environmental impact index. I think of this as, for example, the energy efficiency index that perhaps our fridges all have, the A+, A++, and so forth. So if we launch, and this is something that in some ways had already been proposed and developed, but more in terms of resorting to more ecologically green launch services that do not use highly pollutant fuel and oxidizer, for example. We can also do something along those lines with regards to the materials you use in spacecraft. As the manufacturer or as the prime contractor of the spacecraft, you know what materials are going into it, and you are responsible for the choice you make. And so equating this into the design stage could be something that would be beneficial for all of us. Second point, alternatives. So during this design stage, we may get to the conclusion that this material is not appropriate or that is highly pollutant. And if you want to go back to the aluminum story, what are the alternatives for an aluminum structure, for example? There are not that many, unfortunately, and clearly the world has now moved from aluminum chassis in cars or in supercars to carbon fiber reinforced polymer chassis, and we may, and it's already happening in the space industry as well. We can do that with with spacecraft. The question being whether this is going to be beneficial in the long term. We know that usually high pressure COPV tanks, so these carbon fiber tanks, usually they tend to survive re-entry, because, and it means that we will increase the risk of hitting people on the ground. And even if they don't survive, I think there is not enough knowledge about how these carbon particles, and whenever we talk about carbon in the atmosphere, some alarm bells ring, because, well, CO2 is not really a good gas for us when induced into high concentrations in the atmosphere. So I believe that these reaction paths for carbon upon thermal ablation during re-entry should also be better understood. I think a year ago, there was a Japanese initiative that launched a wooden satellite to orbit, which was very cool. Which also raises the same question to me, because it's carbon based, and some studies mention that black carbon, even at high altitude, is even more potent in terms of global warming potential. So these are all question marks that point to the fact that, again, this is always going to be a trade-off. And I think the only clear answer that shows us the way forward is that, well, launching less, perhaps going a little bit back on the miniaturization approach and having a little bit of a bigger satellite, more concentrated in orbit, could not be a bad idea. But in the long term, and this will also support efforts for further exploration of the solar system, is the development of an in-orbit circular economy. We will need to start developing the capability of reusing, refurbishing, recycling stuff in orbit, having fuel stations to do it in orbit, having the capability of assembling in orbit. That's the only way forward, not only to clean the orbital cluttering that is already there, but also to start to decrease the amount of expendable single-use items we develop to just put it there and then have it re-entering back in the atmosphere. I'm not saying that this is going to be feasible in 5 years, but I believe that the effort is being put right now in close proximity operations, in rendezvous with docking mechanisms in orbit, shows us the way that perhaps in 10 years we'll have feasible solutions to have it done, and also in an economically sustainable way. Because once we start doing this, we'll be able to decrease the investment we need to do in new spacecraft platforms. We could just start reusing it, and this will open doors to other further developments in exploratory terms of the Moon and Mars, for example. So I don't really have a concrete answer for the short term, but I would say for the medium long term, I think the answer is very clear, and it's hopefully, and it's clearly going to promote sustainability in the long term. I believe we're getting there sooner or later.
I love your optimism. I'm going to have to borrow that in future talks. A world in which we have recyclable orbital stations for capturing like old things and repurposing them. I love that. I've wondered if it's at all feasible to try to convince multiple companies to share a single satellite, akin to how cell towers work. Saying, okay, like, we're going to launch 500 of these things, like all for you, like put your box on it or whatever the case may be. But you don't each have to launch your own. But I don't see a feasible way to do that. But I feel like it could almost be a baby step towards your vision if there's some way to twist arms.
Totally. And I've heard of some initiatives trying to push for that, like the satellite with a shared payload that you can just essentially borrow time using that payload for your own mission. That's already, I'm not saying that it has a huge market share, but that's already being tried and developed. Also, satellites with a monolithic platform to which you can actually add your own payload, so that you don't have to purchase your own satellite bus and then develop everything from scratch. That's also being attempted, and it's in service right now. But again, these are baby steps towards that vision, which I deeply cherish and appreciate. And also, not only that, but also the effort of being able to refurbish and extend the lifetime of satellites in orbit, which are most times limited not by technology, but because they run out of fuel. You need fuel to perform these collision avoidance maneuvers. In geostationary orbit, you need fuel to actually keep the station, do the station keeping for your satellites. And this has been attempted in the geostationary orbit. There were a couple of mission extension vehicles that were able to dock with those spacecraft in orbit, with those satellites, and refuel them, which is absolutely outstanding. So that's why I'm optimistic, because some of the key breakthroughs had already been proven. And I believe with some goodwill and investment, we will get there.
One can hope. That's awesome. What about sorry, Mark, I realized we were just chatting with it. Maybe that's what you wanted. What do you think about the fact that space is a harsh environment? Like, how does that affect the recycle everything dream? Just because everything gets holes in it, and chemistry happens in ways that I don't fully know.
That's a very good question. Usually, with regard to space environment, I'm concerned about electronics, and truth be told, recycling electronics, even on ground, it's a little bit difficult, to use an euphemism with a little bit here. It's complicated to recycle electronics.
Yeah, just throw the batteries in a heap. It's fine. Yeah.
So I would say that to start with, it would be with recycling like the crude raw materials. I mean, if we look at the aluminum, for example, or the metals, we can think of that. I think there are a couple of initiatives trying to develop some sort of forge foundry in orbit, although it's difficult because of the power requirements, as you can imagine. I can also see solar panels being refurbished if you just replace, or if you're able to replace, for example, the cover of the solar panels, so essentially shielding them again. Although, of course, solar cells have some sort of their efficiency decays as a function of time, so that would also be difficult. But if we're able to get it back with some new refurbishment of the surface, that could also be a potential way forward. Antennas, for example, if I'm not an expert in RF, but if the deployable mechanisms are still functioning, I don't see a reason why we couldn't use it further. But for sure, electronics are the biggest concern. Chemically speaking, if you are at the very low altitudes, I would be concerned with atomic oxygen impingement and erosion and so forth. At higher altitudes, of course, you'll need to pay attention to plasma interactions with your spacecraft and arc discharge and so forth. But on the chemical level, it may not be as complicated as we may think. But I would leave that to another expert to dive into, because I'm not very comfortable on the chemistry side. I'm more on the chemistry of what happens when it re-enters in the atmosphere. And given that the environment in orbit is a little less atmospheric intense, with more vacuum than anything else, I would refrain to make many more comments. But if we don't have many atmospheric components and it's mostly vacuum, I would only be worried with high energy particle interactions, plasma, and so forth.
Sure. I will say it was very interesting as an astronomer to watch a bunch of satellite operators discover that there is a solar cycle that happens every 11 years, in which our sun, goes through every 11 years, lots of sunspots and activity and plasma, all this stuff of space weather. Space weather is real, and the satellites had only been up for about half of a solar cycle when we hit solar maximum, and literally none of them knew about this, which was fascinating.
Really?
and mildly terrifying. Yeah, now they do.
Right.
it changes a lot of things. I mean, it changes atmospheric density, or our atmospheric shell is essentially like our lungs.
The drag got so bad
Yeah.
that some just fell out of the sky, basically, because they didn't have enough fuel to counteract. But it also it increases concerns about collisions and debris, because basically what you have when you have a big space weather event is you have all of the satellites are experiencing more drag, and so they all start firing their thrusters as hard as possible to raise their orbits, and so they are all moving as fast as possible at the same short period of time. So collision avoidance becomes like extremely hard, and so I don't know. In 11 years, we're gonna have a wild ride.
Let me interject with one question. Do you think the FCC's 5-year rule is excessive?
Is that for me, for Meredith?
For either.
For both
of you.
Excessive how? Like, it's too short or too long, or
too short? Should it be longer? I mean, Jose, you're talking about a cycle that would be more sustainable than 5 years. But as you said, but every country has its own, or different countries have their own regulations. Is the 5-year extreme?
I do think the 5 years is a good precedent that we can actually get some kind of rule like this applied across the board reasonably well in the name of sustainability. Even if it doesn't necessarily tick all of the boxes. I do think that despite some ancillary effects, that it was an important step. But Jose, jump in with what else you think.
So the 5-year number didn't come out of the blue. This was part of an interagency study. There is this interagency committee, and this has been something that has been discussed, and this is where the 25-year guideline comes from. Essentially, how should I say this? The more proactive space agencies around the globe had come to the conclusion that the 25-year limit to the orbit is what would be the bare minimum in terms of preventing the orbital environment. Essentially, something along the lines of the 1.5 to 2 degrees Celsius increase in 50 years to prevent a catastrophic or irreversible change in climate. So something along those lines. But again, those are both guidelines. I mean, and as of now, and to my awareness, FCC was one of the first, if not the first, national regulator to implement it as a rule, not as a guideline. And they did not implement the 25-year rule; they implement a 5-year rule. And how did they come to the 5-year number? It's not really clear to me. But it's definitely, I mean, it makes sense when it comes to preventing orbital cluttering in the longer term. And as I mentioned in the beginning, this is always going to be a race between what comes to the ground, what stays up, and what stays in the atmosphere. We are in a closed system, and therefore mass will always be conserved. So whatever doesn't stay in orbit will come to the ground or will stay in the atmosphere. So to this point, it's difficult for me to say it's excessive, because it's excessive to what ecosystem? It's excessive to the atmosphere, to the ground, to the orbital environment. It is always going to be a trade-off. I think we are going in the right direction in the sense of limiting the amount of time that objects stay in orbit, because if they stay for too long, and then if we are not able to control them after they terminate their mission, then we have a problem. Because if we have a catastrophic collision, and then we have this cascade effect where the smaller particles may impact other satellites, that is a very complicated problem that we cannot fix.
Right. A gravity scenario.
Exactly. The gravity
syndrome. Yeah.
As for what comes next, and as I mentioned earlier, I believe we need to understand more in depth about what takes place to be able to answer that question, which was spot on, but to which I need to be intellectually humble to say, I don't know.
Fair enough. We've talked now the bulk of the hour. I just want to ask one more question. We've talked this whole time without actually even talking about the change to the visual night sky, just the effect of going out on a clear night, and what we may see, the way that is changing because of these satellite mega constellations. I mean, if all the proposals for these mega constellations come to fruition, Meredith, I'll start with you and then to Jose, but what are we really going to see when we look up, and what are we losing?
Yeah, the night sky is fundamentally changing. And that is one reason that I care so much about this work, because nobody really consented to this fundamental change, right? Since, used to, everyone could go outside and just see the Milky Way if it wasn't a cloudy night. And then, the electric light has many good applications. I'm not arguing against electricity and lights in general, but it really did fundamentally change humans' relationship with the night sky. And now we're seeing another kind of shift in just what people expect when they go and look up. And there is a really powerful simulation that a colleague of mine has made where you can use one of those VR headsets, and it shows you what it looks like on an otherwise clear, dark night sky with 40,000 slightly brighter than Starlink satellites swarming around in low Earth orbit. And it is an uncanny swarm kind of thing. And I've experienced like miniature previews of this when I'm just trying to take my kids out to look for. Like, we have a roof deck here in Seattle, and when we get a miraculously clear night, sometimes the kids will say, "I want to get the little telescope out," and I'm like, "All right, let's go." But when trying to point at Jupiter or whatever, and it's low in the sky, when you're trying to get it in the eyepiece, you see these satellites just kind of going by, and then because they're kids, they're like, "Ooh, what was that?" And you're just like, "It's a satellite. That's not the cool thing." The cool thing, unfortunately, holds still. It doesn't catch your eye, like, out of the corner of it. So it's, that's my own personal experience of it, but it's not great. I don't love it.
Jose, do you have any thoughts on the way that this is moving?
First and foremost, what part of the process of getting licensed to launch a spacecraft to orbit goes beyond the intentions of what is planned. So even though there are these plans, and these companies filed for allocation, for spectrum allocation and so forth, from that point to actually launching the spacecraft, the actual national regulator needs to allow them to do so. And this is and it's also part of the responsibility of the national legislator to demand pieces of evidence with regards to whether or not there are some sort of impacts. And as a matter of fact, FCC has done that, or has been requesting operators in the US to do that. To what extent these environmental assessments what's the detail of these environmental assessments may be debatable, in the sense that whether they are accurate, technically sane, or technically feasible in the end. But at least national legislator here in the United States had shown that this is the modus operandi as of now. So in that sense, what I'm trying to say with this is that even though these plans are on the table, I think there are still a lot of steps that need to be confirmed to reach to that reality. If we reach to that reality, I would be very surprised if we don't have in place a framework to mitigate the impacts, not only in the dark, quiet skies to astronomy, but to the whole environment. Because this is not going to be just a potential hazard for the atmosphere; it's going to also to be a potential hazard for situational awareness in orbit. I would be very surprised that with this amount of pieces of active objects in orbit, we would be able to coordinate them all accurately, especially when in presence objects that are already defunct, non-operative, and that are non-cooperative, most of all. So even though, I can totally see a reality where the active satellites can totally avoid each other, in the sense of similar to how automatic self-driving cars work. But I think the problem here would be the capability to detect the ones that are non-cooperative and to be able to avoid them. I believe those are the most harmful ones in the long term. But still, my positivism here goes even beyond to the fact that I trust that the regulators will play their role by asking the right questions and preventing any sort of harmful orbital deployment from happening if the answers are not satisfactorily answered with regards to all the questions that may be asked during the process, not only with regards to the environment, but also with regards to maintaining a sane operational environment for all the assets in orbit.
Well, I think that positivity is a good note to end on. So, Meredith and Jose, thank you both for joining us so much. I really appreciate it.
Thank
It
you,
was
Mark.
a pleasure, Mark. Thank you, Meredith.
All right. And stay tuned for more SpaceWaves.